Hello, this is Dr. Greg Wagner with the last video lecture for this class, which is lesson number 9, Inference on First-Order Logic. So basically what inference first-order logic is converting first-order logic into propositional logic. Propositional logic is much easier to code up. First-order logic would be kind of, if you took philosophy, it would be kind of more like informal logic, whereas propositional logic would be like similar to formal logic. So this lecture is basically going to go over a few things: reducing first-order logic inference to propositional inference, unification, which is kind of how you combine different things, generalized Modus, Ponens, forward chaining, backward chaining, resolution. So basically, how to kind of do the inferences from first-order logic to propositional logic using a few techniques. So if you want to convert the universal instantiation, remember the upside-down A, in first-order logic to propositional logic, what you basically do is combine, substitute all the values of A, of V in this equation into A. So for example, the first-order logic, in all cases, X, King X, or greedy X implies evil X, yields. So we have John and Richard as X's. So this would basically, in propositional logic, be King John or greedy John implies evil John, or King John, or King Richard or greedy Richard implies evil Richard, and the King Father of John, or King greedy Father of John equals evil Father of John, so on and so forth. So basically, all your propositions or variables would be put in here, and you have instantiate all different cases. And then remember the backward Z, or existential instantiation. You would basically substitute the value of A for K again. So for example, there exists X for crown X, or on head X of John yields. So you have the crown C, or on John of crown C. So basically, just again, instantiates a different constant, and this is called the solemn constant. So it's a symbol that's going to basically replace all the different instances. But notice here, there's not all the different cases. Basically, you just have a constant variable. So that's the constant variable is just the one case, and you can't see it on video because I didn't turn video on, but I was doing it on one finger, so I kind of feel silly about that since this is you don't have a video being playing. But again, this constant value is called the Skolem constant. So basically, when you translate from existential instantiation, you basically just put a constant value in for X, because that now will be the one case, at least one case. And then what I was saying is K does not appear elsewhere in the knowledge base. It just appears in one place, so that's why you make it a constant. And then, so to do the reduction of propositional inference, suppose that you have the knowledge base contains the following. In all cases, X, King X, or greedy X implies evil X. And then so you have King John, greedy John, and brother Richard John. So instantiation in the universal sentence, in all possible ways, we basically just put King John in for one case, Richard in for another case, and then we still have the actual kind of basic sentences: King John, greedy John, and brother Richard John. So we have these cases, and since these guys are joined, that's why we have cases in both cases, because we imply that the brother in this case is also the king. And so what I'm saying down here is the new knowledge base is propositionalized, and the proposition symbols are King John, greedy John, evil John, King Richard, so on and so forth. So we also have greedy Richard and then evil Richard. And my mistake, this implies the king is greedy. I've been saying or, this is and. And so reduction can be used for every first order logic knowledge base can be propositionalized so as to preserve the entailment. Then I say in the parentheses, a ground sentence is entailed by a new knowledge base if and only if entailed by original knowledge base. So basically, if you have a subset of that original knowledge base, you can put it within an existing knowledge base. And then so the idea is propositionalized knowledge base inquiry imply resolution and then return a result. So basically what you do is you propositionalize a knowledge base and then you can query that data and then get some sort of result. And this is basically how the logic language like Prolog works. And then every knowledge base can be propositionalized so as to preserve the entailment. And then, this is the next slide. So the problem with this is with functional substances, there's infinitely different ground terms. So you can have implied ground terms and stuff like that. So what that's saying is you could basically in computers, in theory, you can have an infinite number of symbols. But in real life, you can basically only have as enough as your memory can store. And usually you just try to limit the scope as much as more than that. And then this one theorem, so this implies kind of like philosophy and Boolean algebra. And so this stuff has been around for a long time. I was pretty amazed when I first started learning about like Boolean algebra. How this stuff has been around since the 1800s, early 20th century. And computers really haven't been invented yet. So this technology kind of came back to life in the 1940s when computers kind of were there. So these people are way ahead of their time as far as the math that ran computers. And so the Herbrand theorem is if a sentence alpha is entailed by a first order logic knowledge base, then it's entailed by a finite subset of the propositionalized knowledge base. And so the idea is if you have a number of terms n to infinity, create a propositional knowledge base that is stand state with depth n terms and see if it's entailed. So basically what you do is you keep on increasing the number of terms, and then once it finally instantiates the total knowledge base, then you stop. And it can go to infinity, but unlike computers, since we have a finite number of memory, basically it goes until you run out or you kind of run out of terms that you're using. And the problem is it works if alpha is entailed, and then it keeps on looping. It would keep on looping until alpha is not entailed, but basically you run out of memory before that happens. And then we have a couple other theorems. We have a Turing-Church entailment for first order logic of semi-decidable. So basically, you can entail all first order logic if they're semi-decidable algorithms which it means algorithms exist that say yes to every entailed sentence, but no algorithm exists that also says no to every non-entailed sentence. So basically you have a set of sentences that are within the set, and then basically you can kind of ignore the ones that are not. And then, so the problems with doing propositionalization is basically you're creating a lot of sentences that don't exist, basically so to make sure that you entail stuff. So that keep on like the idea that you keep on growing on the previous slide until you tail everything, but a lot of stuff paths will never go in. And this is also an idea in software engineering. So software engineering, if you guys ever work on a big software engineering project that has millions of lines, you'll look at the computational complexity, which means that you're going to have so many if statements in the program, or so many paths to go down, that there's some paths that you can't check everything because they're just so complex. You can't check every single path. And so if your computational complexity is so high, computational complexity is so high, or you won't be able to check everything. And so you might have cases that the path never goes down except in really rare cases, and then if it crashes then, because you weren't able to check it, that could be a problem. And so the idea is also with this, is that if you have a lot of irrelevant sentence stuff that never really gets checked, why do you have them? So you might want to get rid of them because the size is so big. But a lot of propositional algorithms entail them just in case, even though you may never use them. And then, so in this case, you have John as the king, But if you calculate, Richard is greedy, but you have to be both a king and greedy to be evil. Why does this logic exist? And that's kind of the idea behind that. And then the complexity is with p, k array predicates, and n constants, there's p times n instantiation. So basically it just kind of limits how big. And so the two propositions, p and q and theta. And so to get the theta value, we're going to basically infer knows John of x. So we're going to put in here x is basically x is Jane. X is Jane. You can see that here. So for the proposition, John knows x, and then we can fill in the variable, and then with the other query, John knows Jane. And then we know that John knows John x, and y knows OJ. So we have this thing that this proposition, John x, y OJ. So we have basically x is OJ, and then John is possibly x is possibly OJ, and John is possibly y is possibly John. And so we have this instance of the knowledge base of John knows x, knows y, knows mother of y. So we have this case that we know that y is John, so we know that x is the mother of John. And now we have this case where John knows x and x knows OJ. Well, we know that y is Jane, right? And then it doesn't really match up because we don't really know if John knows OJ, and so this is a fail. So the unification in this instance, for this particular case, did not go through. And so to unify John knows x and John knows xy, we get the theta y of John, x of z, or y of John, x of John, or z of John. The first unifier is more general than the second, but it covers all the cases. And so there's a case that the most general unifier that is unique and remains to all variables. So in this case, the most U case is this one. That basically ends up renaming the variables. So we have y is John, but we also know that x and z could also be linked as well. And so this is the unification algorithm. And it returns substitution to make x and y identical. So basically what this does is it tries to find the different paths to go down and unify. And then here's a further expansion of it. And then examples of unification. So we have the parents. So we have y, father of x, or the function father x, mother of Bill. And so the parents of Bill is father of x, Bill, parents, Bill, father of Bill, and y. And then we can get the unified theory that x is Bill, and then y is the mother of Bill. The way we get that is basically by passing these values in. So we know in here we have x, this equivalent to Bill, and we have father of x, which is the father of Bill, and we have the mother of Bill, which is y. So in this case, we know that y is the mother of Bill, and that x is Bill. In other examples, we have the parents x, we have the father x, and the mother of Bill, and we also have this function again, or this sentence again, parents of Bill, father of y, and z. So the most general case is, well, we know that if we follow the instance again, that x is going to be Bill, and we also know the father of x is Bill, so we know that y is Bill, and we know z is the mother of Bill, so we have these sentences here. So again, the parents would be child and the parents. And then another example is we have x, father of x, and mother of Jane. So if we define x as Bill, and we're the father of y, so that's probably going to be Bill, but we're the mother of y. And so we have different parents here. We have Jane is probably going to be y, and Bill, but we're not certain in this case that Bill that the father of Bill and the father of Bill and Jane's, the father and mother of Bill and Jane are both the father and mother of each other. They could have step parents or half brothers or something like that. And so the Generalized Modus Ponens GMP is P1, P2 through Pn, P1 through P1 and P2 Pn. This is the general theorem of it, or the generalized theorem. And so in this case, if we have P1 prime is King John, P1 is the king of Y, P2 prime is greedy, P2 is greedy, then theta is, in this case, X is John, Y is John, and then Q is evil. Then basically the sentence would go, Q theta is evil John, because we know these are the same people. And the generalized Modus Ponens is used with the knowledge base for definite clauses, exactly one positive literal. And so all variables assume universality is quantified. So what this is basically saying is you can use this theorem up here to calculate p theta. And just to be clear, I know I haven't supposed to say this, basically the above the line is what defines what is the below the line. It's not division. So in this case, John defines X. Y defines John. And the soundness of the GMP is, well, basically I have the proof of the theorem, is we apply these different limits. So we need to show that this here on the left is logically equivalent to Q theta, provided that we have Pi prime theta equals Pi prime for all I cases of I. And so for any sentence P, we have P logically equivalent to P theta by universal inference. We can basically apply these different things by we have this implies, this on the left implies this on the right theta, and then we work this in. And then we have the same thing with the prime values, and then 1 and 2, Q theta follows an ordinary Modus Ponens. So basically it's saying, okay, if this is true and this is true, we probably have a generalized MP. And so the final example is the law says that a crime for Americans to sell weapons to a hostile nation. The country, no, an enemy of America has some missiles, and all the missiles were sold to it by Colonel West, who is an American. So we want to prove, based on this logic, if Colonel West is a criminal, basically saying that Colonel West is American and no is an enemy state, and if Colonel West sold weapons to the criminals, how could we, to the no state, or to an enemy state, is Colonel West a criminal? We're going to basically try to prove that using first-order logic and then a propositional logic. So it's kind of just a big example. So to convert the sentence into a first-order logic, we have American X and weapon at Y sells X, Y, and Z and hostile Z implies he's a criminal. No has some missiles, such as there is an X owns no X, and X is a missile. So basically this line is saying this country owns missiles. And then all the missiles are sold by Colonel West. So basically saying if someone sells a missile and they have it. So missile X and it's owned by no implies that West sold to no. The reason why this is because West is the only person that can sell those missiles. And then missiles are weapons, so it's illegal to sell weapons. And defines American counts as hostile. And so enemy X, if X is the enemy of America, and then it's hostile. And then West is an American, Colonel West is American, The country no-no is an enemy of America. So it's converting to more have a propositional logic. And so there's basically two ways we improve this. We use the forward chaining algorithm, which we talked about last week, which goes from your goal state down to the all the initial propositions, or we can do back chaining, which goes from the initial propositions and then it's a bottom-up approach. Or I'm sorry, we have forward chaining is where you have all the initial states and you prove that the goal state. Back chaining is where you have the goal state and then you go back and prove it. And one thing I want to say about the difference between like forward chaining and back chaining, they're not mutually exclusive. A lot of times I'll see really complicated logic, and computers are a lot better at this. They'll start at they'll start at the back chaining with a goal, and they'll some start with the goal forward chaining, and in parallel they'll move towards the center, and then if they get stuck, one of the chains hopefully will link together and they can finish it off. So in this case, we have the definition: Colonel West is an American. There's a missile M1. The country no-no owns missile M1, and the country no-no is the enemy of America. So we imply that missile M1, or a missile is a weapon. Missile was sold by Colonel West. Colonel West sold missile M1 to no-no, and since no-no is a and this is implied. The second one is implied, basically saying because M1's a missile and no-no owns M1, that West sold a missile to no-no, and this is hostile becomes a no-no. And so we can imply that West is a criminal based on all this, saying that since Colonel West is an American, and it's illegal to sell for Americans to sell weapons to countries that are enemies. An enemy country, no-no, has a missile, and it's an enemy because it's hostile. Right? Colonel West is a criminal because he sold missiles to no-no, the country. And so, use the first order logic, kind of translating into propositional logic. This is a sound and complete first order definite clause. Then the data log is the first order definite clauses and no functions. So the forward chain terminates the data log in infinite numbers of iterations. It may not tame in general if alpha is not entailed, but this is unavoidable. Entailment with definite clauses is semi-decidable, which means that there's at least a path that goes through it. So the efficiency of forward chaining, incremental forward chaining, there's no need to match a rule on iteration k if a premise wasn't added on iteration ki. So basically, as long as you keep on not starting to keep on adding anything, you don't need to match a rule. And so matching can be expensive because you basically have to go through the database and find it out. But if you index, matching can be expensive, but actually pulling from a database is fairly computationally inexpensive. Basically like pulling from a hash table, so it can be pretty quick. You just need to know where to look. And so forward chaining is widely used in what's called deductive databases. Basically, you have a set of items, and then you want to interpret how the goal to be. And so in one instance of this, is we have a hard matching example. So this is a case we're doing basically the coloring again. And so colorable is a function that is inferred if and only if the CSP, or the constraint satisfaction problem, has a solution. And the CSPs include 3SAT, which is a special case, hence matching as NP hard. So basically saying to try to match all these could be computationally difficult. So what this is doing is basically saying, okay, we have all these differences, and we have to try to get them to match these different patterns, and then it would be considered colorable. And then backward chaining, if you remember from before, and I said it just a few minutes ago, is basically you start with a goal, and then you kind of go backwards and chain until you actually get the initial propositions. And the idea is you substitute a compose of theta 1 and theta 2 with P, and then you substitute at least one of the values with one of the other ones. So I have this idea. Someone is a criminal. And this is what defines a criminal. If someone's an American, someone sells weapons to an enemy, and then the enemy is defined as hostile. And in this case, we define x as west. So it's going to feed forward and put x into west, and it's going to null terminate. And then we're going to say, okay, a weapon is defined as a missile based on the logic we have been given. And then we define M1 as a missile. So we got M1 as a missile, and it's going to back propagate to all these different locations. So notice here we have Z as a no-no. So we have these values propositioned here, and we're going to plug in these values. And then we get a null termination as this value gets plugged in and pushed up. And we've basically defined backward chain as example. So notice here we kind of have a little bit of extra inferences here. And so backward chain is a depth-first recursive proof. The space is linear and the size of the proof. It's incomplete because it could have infinite loops. And it's inefficient due to repeated sub-goals, both to sexes. And this is widely logic programming. And so it's widely used, not only logic programming, but it's also used a lot for compiler construction. And so the logic programming language is what was widely used is a Prolog. And I'll put a link to a free Prolog interpreter that you can download in one of the links below or for this presentation. So the algorithm is built up with logic control. Basically, we do the backward chaining, use the Hahn clauses, and a few bells and whistles. Prolog is really, really popular in the knowledge-based community. In grad school, our knowledge base lab for grad school, like the AI lab for knowledge bases, was right next door to mine. And all those dudes use Prolog, or I guess all those dudes and dudettes use Prolog. And I worked in a computer vision lab, and we almost exclusively used C++. And so the knowledge-based guys, which were all a lot smarter than us, admittedly, it's kind of like, kind of pure AI or knowledge-based, in this case, knowledge-based AI, people are a lot smarter than us. Kind of like if you ever watched Big Bang Theory, where Sheldon makes fun of whatever the other guy's name is, the other physicist, for not being a theoretical physicist because he's an experimental physicist. It's kind of the same thing. The theoretical guys in artificial intelligence made fun of me in the applied AI fields. So anyway, basically, Prolog is a logic programming languages, and it's pretty much the only one that I know of. Basically, you have a program, so you have a change of clauses, so you have a bunch of heads, and then you would define it. So criminal would be defined as American X, weapon X, cells X, Y, and Z. And then you have the depth first, left to right, backward chaining, built-in predicates of the different values, and you can have some arithmetic in there as well. And then these are predicates that have side foot, they have input, output, and then the closable assumption, negation as failure. And so given alive, not dead, kind of like, this would be like Schrodinger's cat sort of thing. But basically you could build up a programming language like this. And so for Prolog, unfortunately we don't have time to do this assignment, but if you want to do one for your project, if you haven't got one, if you haven't proposed one yet, you could definitely do something in Prolog. Appending to lists produces a third list. So say if you append L to YZ, basically be adding these types of values, and you kind of get these basic definitions. So append A, B2, the answers would be, you have empty set of A, B is 1, 2, you have A, it could be 1, B2, or B3, so you basically have these 6 different sets. And then so for resolution, again, the brief theory is you kind of have these L logic theories, M logic theories, and then it produces, basically would produce this set where you can unify N and L and not M. The clause would be subsized, basically saying, okay, if you're not rich or you're unhappy, Ken is rich, so imply that and Ken is unhappy would imply that he might be rich. So if you're not rich, or you're unhappy. Rich, and Ken is rich. He could still be unhappy, would kind of work out. And this is a little bit clustered size, but the conversion to CNF, where everyone loves all animals is loved by somebody, will convert to this kind of first order logic equation. For all x, for all animals, implies all animals is loved by somebody. And this eliminates the biconditional. So first you eliminate the biconditionals implications. So we get rid of the biconditionals here, and then move inwards, kind of applying these different values. So it kind of build into this space down here, where in all cases there's at least one case where someone loves an animal for all the different types of cases. And then for this, I didn't work on counting, but for the third step, standardized variables, each quantifier should be a different one. And so you have these different quantifications, and you sologamize, basically a more general file of essential instantiation. You saw I defined this earlier in the previous presentation. So basically it encloses it in step 3, part 2. And you drop the universal qualifiers, so we get rid of this qualifier, so that it becomes this. And then you distribute the ors across the ands, and you kind of get this definition. And so, basically what this is saying is there's basic steps to convert first order logic to a CNF format. And then we kind of have these different steps to do this this final clause. So we have this. So we have these prepositions here. If you're not an American, you don't, or you're not selling weapons, or something's not a weapon, or you're not selling it, or something's not hostile, or not something that's criminal. And we're basically starting off with West is not a criminal. So we're basically starting with the subject of guilt. We define West as an American. So we're going to say, is West not an American? Well, that kind of is contradictory. So we're going to get rid of that one. And then we're going to say missiles, if you're not a missile or it's not a weapon. And so basically we're going to define, we're going to define West as a criminal. And since it's not, so we're going to define West as not a criminal. Well, if something's a missile or it's not, basically we're going to get rid of, if something's not a missile, it's a weapon. So basically say, okay, if it's not a weapon, it's not a missile. You're going to find a missile as M, so M's going to M1 is going to replace Y, because that's what you're selling to. And basically we define M as a missile, so the missile clause is going to disappear. And then we have these definitions. That's not a missile. It's not owned by Nomo. So we're starting to eliminate stuff, and West sells to Nomo. No, I mean. So if something's not a missile, something sells no. We're going to basically fill these values in for here. So we basically say if it didn't sell, well, no can't have missiles, nor is it hostile. So we're adding a little bit of a clause here. And then again, we define M as a missile. So we're going to say, okay, this eliminates this one, so we got this. So if basically saying, we have evidence that no owns a missile. Well, if that contradicts that one, so we eliminate that one. And then we're saying, okay, if it's not an enemy of America and it's not hostile, well, there's this hostile one. So basically it's saying the enemy knows America. These define each other and they cancel each other out. So it's basically saying West is a criminal using the definite clause theorems. So that's all I have for this presentation, and this is my last lecture for this class. If you have any other requests for stuff you'd like to see for this class, please message me and I will try to put something together, or just talk to me. Hope you enjoyed the material, and I guess watch some of the other videos if you're interested.